So the first idea that I want you guys to learn today is the idea of dimensional analysis. So uh, just as if you're doing algebra, you want both sides of an equation to have valid numbers, right? 5 plus 5 equals 10. Those must be the same. In physics, well, if we're describing things that are physically existing, they have dimensions. Like if I describe the mass of my phone and I had that in an equation with some other things, both sides of the equation have to have the same exact dimensions. So if one side has the dimensions of meters per second, the other side must also have the same dimensions. And there are some other ideas that we can come out of this, which is the argument of an exponential, logarithm, or trigonometric function must be dimensionless. So what does this mean? Well, if you guys know about trigonometric functions sine, like sine of x, there is no meaning to, I guess, having a dimension in x. So if you actually think about it, if x had dimensions of mass, what does it mean to take the sine of a mass? Because the sine function, takes in an angle, okay? And angles don't have any dimensions. So the argument of the trigonometric functions cannot have dimensions, as well as the logarithm, such as the natural log or the exponent. So this is a good way to check that if there's anything inside, if you have an expression with any argument x that's in one of these cases, it has to be dimensionless. So if you have something with dimensions in one of these functions, then something went wrong. So in the same vein, dimensional analysis can always be used to check your answers and can sometimes be used to solve a problem entirely. And I'll give you an example of that on the next slide. And something more advanced is that dimensional analysis can be used to solve integrals, but you can look at the problem set for more about that. Any questions so far? Just feel free to unmute your mic because that's the best way.
Aren't there some expressions for like where the natural logarithm does have dimensions? Like I know sometimes you have to take the natural log of mass, I've seen.
You'll never need to do that. So, because it has no meaning in a sense, because the function itself, the argument of that function, like I guess the definition, the idea of this function, it doesn't have any physical meaning. So what you put into it cannot have dimensions. So you will never actually encounter a case where mass goes into the argument. Any other questions? Cool. Okay. I'm going to give an example. So this is kind of a simple example, but this example is how it teaches you how you can solve problems using dimensional analysis entirely. So if you guys have heard of a simple pendulum, it's like a bob on a string and we can swing it. And it has some kind of period t, which is the amount of time it takes for it to start at a spot and swing back to that spot. And this time depends on its length and the acceleration of the gravity g. And the problem says up to a dimensionless constant, find the period t in terms of L and g. So what we can do with dimensional analysis is to find the relationship between different variables, but we can't find the actual numerical prefactor that goes into that. And I'll talk more about that after I go through this. But we know that the period t has dimensions of time. Length is just length. And acceleration due to gravity, the dimensions of acceleration is length over time squared. Okay, so we want to find t, and this is a function of the two variables that are going into this situation, which is length and gravity. And these, so we want to find the relationship between these, which means these two variables both have some kind of power associated with them that feed into the equation for our period. So let me define these powers as alpha and beta, which means if we find alpha and beta, our equation is just going to be length times alpha, g times beta. And then after doing that, we found the relationship between all the variables. But now we must notice that the dimensions on both sides have to be the same. Clearly, we have no dimensions of length on the left side. So essentially what happens is if we were to simplify this, we have L to the alpha plus beta over t to the 2 beta. Okay, and this has to equal t. We can see that there's no dimension of length on the left side, which means alpha plus beta must equal 0. But we can also see that the dimension of time on the left side is 1. So negative 2 beta equals 1. So we can find that beta equals, well, negative 1/2. And alpha from the other equation equals 1/2. So if we have alpha equal 1/2 and beta equal to negative 1/2, we can plug these into the equation here. You have the square root of L over G. And this is actually the correct expression for the dependence of T on L and G. Like if you have a longer pendulum, the period will be longer. But the problem is that the actual equation has a 2 pi in front here. And we couldn't find that through dimensional analysis because the number 2 pi has no dimensions. So one limitation of dimensional analysis is you can't find the actual expression, but in most cases you can find the dependence of the variables on one another. So if you wanted to, like, guess, write this answer in the problem set, you would say T is proportional to L over G, and this little symbol is the proportional symbol. Any questions?
Wait, could you explain how you got the L over T squared in the first expression, like T is
Okay.
equal to?
Yeah.
Yeah.
So the definition of acceleration is change in speed over time. The dimensions of speed is length over time. And if we do change in speed over time, we divide by time again. And this is the dimension of acceleration. That's just how it's
Okay.
defined. So we're
Yeah,
going to
it
do
makes sense.
kinematics next week. So if you don't know what acceleration is right now, that will come up next week.